Welcome to this comprehensive analysis of critical points and stability in nonlinear dynamical systems. In this presentation, we will explore a system of differential equations, find its equilibrium points, and determine their stability using geometric methods. Let's begin by examining our system of differential equations. We have two equations that describe how the variables x and y change over time. The first equation is dx dt equals negative of x minus y times 1 minus x minus y. The second equation is di dt equals x times 2 plus y. These equations represent a nonlinear autonomous system, meaning the rates of change depend only on the current state, not explicitly on time. Notice the nonlinear nature of this system. The first equation contains product terms between x and y, while the second equation shows a linear dependence on x but nonlinear dependence on y. Such systems often exhibit rich dynamical behavior, including multiple equilibrium points with different stability properties. Now, let's find the critical points, also known as equilibrium points or fixed points. These are points in the phase plane where the system remains constant over time. Mathematically, we find them by setting both derivatives equal to 0 simultaneously. To find critical points, we solve the system of algebraic equations obtained by setting dx dt equal to 0 and di dt equal to 0. This gives us two equations. Negative of x minus y times 1 minus x minus y equals 0. And x times 2 plus y equals 0. We can solve this system by considering cases. From the second equation, x times 2 plus y equals 0, we have two possibilities. Either x equals 0, or 2 plus y equals 0, which means y equals negative 2. We'll examine both cases systematically. Let's start with the first case. X equals 0. When we substitute x equals 0 into the first equation, we get negative of 0 minus y times 1 minus 0 minus y equals 0, which simplifies to negative of negative y times 1 minus y equals 0, and further simplifies to y times 1 minus y equals 0. Solving y times 1 minus y equals 0 gives us two solutions. Y equals 0 or y equals 1. Therefore, we have found two critical points, 0, 0 and 0, 1. Now let's examine the second case. Y equals negative 2. Substituting y equals negative 2 into the first equation gives us negative of x minus negative 2 times 1 minus x minus negative 2 equals 0. This simplifies to negative of x plus 2 times 3 minus x equals 0. We have the equation negative of x plus 2 times 3 minus x equals 0, which means x plus 2 times 3 minus x equals 0. This gives us two solutions. X equals negative 2 or x equals 3. Therefore, we have two more critical points. Negative 2, negative 2 and 3, negative 2. We have now found all four critical points of our system. 0, 0, 0, 1, negative 2, negative 2, and 3, negative 2. Each of these points represents an equilibrium state where the system can remain indefinitely if undisturbed. Now comes the crucial question. What happens to the system when it is slightly perturbed from these equilibrium points? This is where stability analysis comes in. We will use direction fields to visualize the flow and determine the stability of each critical point. A direction field, also known as a vector field, shows the direction and relative magnitude of the flow at each point in the phase plane. By examining how trajectories behave near critical points, we can classify their stability. Stable points attract nearby trajectories, while unstable points repel them. Let's examine the first region containing the critical points 0, 0 and 0, 1. I'll now display the direction field for this region. Notice how the arrows show the flow of trajectories throughout this portion of the phase plane. Looking at this direction field, we can immediately see different behaviors around the two critical points. Near 0, 0, the flow appears to have a saddle-like pattern, while near 0, 1, we see a spiral pattern. Let's focus on the point 0, 0. This is a saddle point. Notice how trajectories approach the point along one direction but diverge along another direction. This mixed behavior characterizes saddle points. Saddle points are always unstable because most perturbations will cause the system to move away from equilibrium. In a saddle point, there are stable manifolds where trajectories approach the point and unstable manifolds where trajectories diverge. The presence of both attracting and repelling directions makes saddle points particularly interesting in dynamical systems. Now let's examine the point 0, 1. This is a spiral sink. Observe how trajectories spiral inward toward this point. The oscillatory approach indicates complex eigenvalues with negative real parts in the linearized system. Spiral sinks are asymptotically stable, meaning the system will return to equilibrium after small perturbations. Spiral behavior occurs when the system has damped oscillations. The trajectories wind around the equilibrium point while gradually getting closer. This type of stability is common in mechanical systems with damping or in predator-prey models. Now let's move to the second region containing the critical points -2, -2 and 3, -2. I'll display the direction field for this region. Notice the different scale and the location of these points. In this region, we see two very different patterns. Near -2, -2, all arrows point directly toward the point, while near 3, -2, all arrows point away from the point. The point -2, -2 is a nodal sink. All nearby trajectories flow directly toward this equilibrium without oscillation. This indicates real, negative eigenvalues in the linearized system. Nodal sinks are asymptotically stable and represent strong, direct attraction. In nodal sinks, the approach to equilibrium is exponential and non-oscillatory. The direction field shows a radial convergence pattern where all vectors point inward toward the critical point. The point 3, -2 is a nodal source. Here, all trajectories flow directly away from the equilibrium point. This indicates real, positive eigenvalues in the linearization. Nodal sources are unstable, as any perturbation causes the system to move away from equilibrium. In nodal sources, the divergence from equilibrium is exponential. The direction field shows a radial divergence pattern where all vectors point outward from the critical point. This represents repulsion in all directions. We now have a complete picture of the stability landscape. We have two stable points: the spiral sink at 0,1 and the nodal sink at -2, -2. And we have two unstable points: the saddle at 0,0 and the nodal source at 3, -2. In physical terms, the stable points represent states where the system can settle and remain, while the unstable points represent precarious balances that the system cannot maintain in practice. The saddle point, while unstable, plays an important role in organizing the global flow structure. From a mathematical perspective, this system demonstrates how nonlinear systems can have multiple equilibrium points with different stability properties. The coexistence of points with complex and real eigenvalues shows the richness of possible behaviors in even relatively simple nonlinear systems. Systems like this appear in various applications including population dynamics, chemical reactions, and mechanical systems. Understanding the stability properties helps predict long-term behavior and design control strategies. In conclusion, we have successfully analyzed a nonlinear system of differential equations, identified all four critical points, and determined their stability properties using direction field analysis. This demonstrates the power of geometric methods in understanding complex dynamical behavior.